Shall I go ahead? Very good morning to everyone. Welcome to the first live interaction session for the course Lighter Than Air Systems. I am Rajkumar Pant, the instructor of this course, and in the meeting also is Mr. Namanuddin, who is the course TA. Although I work at IIT Bombay in the Aerospace Engineering Department, currently I am on a sabbatical leave from IIT Bombay till June of this year, and I am physically positioned as a visiting professor in Plaksha University in Mohali in the Department of Robotics and Cyber Physical Systems. During my sabbatical, I am conducting the same course for the students of Plaksha University, but with a difference. The course is called as Deltas, Design of Lighter Than Air Systems, where design and engineering of lighter than air systems, where we are focusing more on hands-on activities and less on the theoretical activities. So they are also going through the same videos, and but the main activity is to design and fabricate and flight test some systems. Today's meeting, the agenda points are the first item that I will cover is I will give you an overview or a rough exposure to a project on an outdoor aerostat that was carried out in IIT Bombay in our laboratory for an agency called as the IT Development Agency or ITDA of Uttarakhand government. After that, I will look at some questions from Excel sheet. I'll talk about the discussion forum. I'll open the floor for any feedback, suggestions, or complaints that you may have. And finally, if there are any further queries beyond what we have discussed, we will take up those queries. So straight away, without wasting any further time, I would like to go to the aerostat project. Now, this is a hyperlink to another document. So I would like to receive a confirmation that my screen and my audio are visible to you when I go outside this particular link. So can Noman please confirm to me? Are you able to see my screen with the title slide? Anybody else in the meeting can please confirm to me? Are you able to see my screen?
Yes, sir, your screen is visible.
What do you read in the screen?
Relocate aerostats for swift development of communication equipment in disaster-struck zones.
Correct. Thank you so much. That's a confirmation I wanted. So this particular project was inspired by the tragedy that took place in Kedarnath in Uttarakhand, in which, as you all might remember, there were flash floods because of which everything was destroyed. And what you see in the picture on the right hand side is a tower for communication purposes. That tower also eventually was damaged and no communications could be established. So imagine a scenario in which there is a damage to the conventional mobile phone sites, also called as cell sites, which leads to a complete breakdown on a communication infrastructure post a disaster. Now, because many of these cells have stopped functioning, the remaining cells in the area become overloaded, right? This leads to a lot of problem. It does not help the rescuers to reach the communities, and assessment of the disaster zone becomes very difficult. Parallelly, there could be a scenario that in some areas where there are lots of mountain shadows or other other issues, there could be communication dark zones due to which people are not able to use their mobile phones to communicate. So in these areas, it would be useful to have a device or a system that can provide communication. So the mandate that we received from two agencies, one was the IT Development Agency of Uttarakhand government, and the other was from a Government of India agency called as the Center for Development of Telematics or CDOT. They wanted us to design, fabricate, and field test the proof of concept of a system that is relocatable. That means it can be relocated from A to B height adjustable, so that we can find out what is the most appropriate height, keeping in mind the terrain features at a location. And the main purpose of this system is last mile communication. That means communication. Uh, Last mile communication basically means, as I understand, I'm not a communications expert, but what I understand is that you can have a communication available up to some important location, well established location, internet network or mobile phone network. But after that, when you want to take it to some area where there you cannot lay any wires, or where you cannot provide the regular connectivity, that is the last mile. Okay, so our objectives were to demonstrate the system efficacy. That means in case of a disaster, it will be able to send a message to people, 2G, 3G, 4G data and voice communications. We wanted to test the range and connectivity of data and voice, and also the CDOT had developed a new Wi-Fi antenna, so they wanted us to test the efficacy of their Wi-Fi antenna. Then we wanted to also look at the feasibility of this system and also its operational behavior, because there were doubts that when you mount a communication device which works on line of sight below a balloon, and a balloon is always going to shake because inherently it is a system that is buoyant. So will there be a break in communication? Will it work? Will it, because of the oscillations of the aerostat, however we try to make it stable, there will be definitely some oscillations because of the inherent nature. Will that lead to any break in communication? That was the kind of assessment which was to be done. Now, the payload that we were given or we were asked to install, one of them was this high gain radio frequency omni antenna, which can be used for the conventional 2G, 3G, 4G data and voice communication. It was a 4 kg system with a long rod and some connecting devices. And the cost of this was around rupees 85,000. This is one omni antenna. This has to be mounted almost in the vertical condition below the balloon. And from the ground, where you assume that you have internet connectivity, we had to communicate the signal using this RF omni antenna cable. We were asked to provide connectivity by deploying the balloon at a height of nearly 100 meters. And for that, we thought we will like to have a cable of 150 meters length. Okay. This is a very heavy cable. It was 20 kilograms for 150 meters, and the cost was 45,000 rupees. Now, remember one thing, this cable is not actually meant to take a lot of tensile load, because this is normally installed in a fixed condition between 2 points which are very well supported all along the length. Whereas we are mounting it below a balloon, and if the balloon starts oscillating, or because of the free lift of the balloon, you know what is free lift, isn't it? The net static lift. Because of the lightness of the balloon, there will be tension in the cable unless we make provisions to ensure that this cable does not get tensed. And I'll show you that. So the design attributes were that we thought that it's better to delink the two main requirements. The first requirement is the balloon should be able to retain the gas, and the other one is that the envelope surface should be able to bear the load which is going to come on it. So we decided to delink the two features rather than having a single material which meets both the requirements. We thought we will go for a twin chamber envelope. This will have some advantages and also some constraints. Then we did not want to go for uh, you know a classical axisymmetric body of revolution shape that we normally see in aerostats, such as the GNVR shape or the NPL shape or the other profiles. We wanted to make a simple balloon. So we went for an oblate spheroid system. But an oblate spheroid system, as you all might appreciate, it has got less stability, because it is very difficult and maybe not appropriate to mount any stabilizing surfaces on an aerostat. So we went for a sail, and I'll show you how it works. Then, since the system has to be made portable, it has to be easily relocatable. Therefore, We wanted to make the ground handling easy by making the ground handling system completely dismantleable and portable. And to raise and lower the balloon, you need a winching system. And also on the ground, when you don't want the envelope to be up in the air because of any uh, bad weather conditions, you need mooring. Okay. So we designed a quick and robust winch system, which is self-locking and lightweight, and which can be used to lower or raise the envelope. So here is one of the images that can conceptualize the whole system. So you will notice that we are providing internet connectivity from a mobile VSAT terminal which is on the ground, which communicates with the satellite, or any form of backhaul is acceptable here. Okay. Uh, so we are deploying this system in a location where connectivity is available, but we want to use this to provide connectivity in the nearby areas. So the signal from the mobile VSAT terminal or any other backhaul can be communicated via the RF cable to the RF antenna mounted below the balloon. But the balloon is held with a tether, which is a mechanical rope independent of the RF cable. And there has to be a design of the payload carrying bay in such a way that it does not stress the RF cable. Above that, we have this oblate spheroid balloon with a sail. The sail allows it to align in the direction of the wind by getting filled with the wind. Okay, or with getting, it's like a almost like a sailboat. Okay, and on the bottom you can see a small winch with three legs, which can be either pinned on the ground, or it can also have wheels if you want to make it movable. Around that, we have a circular pipe structure on which the oblate spheroid balloon can rest when you bring it to the ground. And then there are guy ropes, which are guy cables, which are used to fit this system to the ground. So basically, it's a sailed aerostat system or aerostat envelope with a sail connected to a mobile VSAT terminal or any other backhaul. Now, these are the system specifications. We went for a bullet spiral envelope, as I mentioned to you. It is better than spherical, but of course, it is not as good as axisymmetric body. But it's a compromise because an axisymmetric body will have higher envelope area compared to a sphere or an oblate spheroid body. So then it will become larger in size. The average deployment height suggested was 60 meters, maximum was 100 meters, and we were supposed to carry a payload of 35 kilograms. As I mentioned, we went for a double chamber envelope, so we were uh, able to request the TIFR balloon facility in Hyderabad to help us with the inner envelope. I would like to place on record my thanks to the balloon facility of TIFR for helping us out with this particular requirement. They actually supplied us the inner envelope, and the outer envelope was made from ripstop nylon, which was fabricated by a company in Navi Mumbai. The tether was supplied by another company, uh, which used braided nylon to strengthen. We were told that the specification of this tether was it can take a load of 2000 kg before breaking. The payload was, as I mentioned, RF omni antenna with RF cable. These were imported, and there was a backhand. Instead of using a mobile VSAT terminal, which is very expensive and also very difficult to rent, we actually tied up with the Reliance Geo, and we got something called as Cell on Wheels, which is a BTS. Now, as I mentioned, two envelopes, inner envelope of low density polyethylene, about 70 cubic meters, outer envelope ripstop nylon, which was made slightly smaller than the inner one so that it is a tight fit. Okay. And the sail was also made from ripstop nylon. Now, to ensure that we never lead to stressing of the RF cable, because there is a joint on the RF cable with the omni antenna. That joint is a very very weak joint, and if any jerk or any load comes on that joint, then there is a very likelihood that the connection will be broken and there will be therefore no communication. So with a lot of planning, we had to get this particular system designed. So you will notice that there is a kind of a semicircular RF cable support tube. So the RF cable is not connected to the central tether point. The RF cable is connected to a curved support cable and attached in such a manner that there will not be any great load in the joint. The attachment ring that you see in this picture allows the envelope to be attached to the payload carrying bay. Then there are some boxes for putting the avionics. Okay. And we also wanted to mount a camera on this system for aerial surveillance purposes. Okay. So this whole system, the payload bay, was designed to ensure safe attachment of the RF antenna without any load and also the antenna cable. It was a lightweight structure. And we also mounted on that, as I will show you in a video, an attitude and weather tracking unit, which allowed us to monitor the weather at the station. Since you are already doing a course on LTA systems, you know that LTA systems are very much affected by changing weather conditions. So it is very important when we deploy them in the field that we get to know what kind of weather we are facing. And looking at the trends, we can also predict what kind of changes are expected to come. Plus, it is very important to know where the balloon is, at what height, is it oscillating too much, what is the sideward movement. So we need to calculate its attitude in continuous. So the design of this system was such that it was safe to handle the stresses which are occurring on it because of the tether. The ground handling system was, as I mentioned, to secure the envelope near the ground and for easy integration of the payload, because when you are mounting something below the aerostat, you are going to stand below it, and therefore you need some support on which the balloon can be rested while you are working on it. And also because it was dismantlable, therefore there were four joints, and therefore it could be put up in the particular station at a very short notice. Okay. Now, this is another interesting thing. The winch that we had to deploy for this particular system also had to be lightweight for easily transportation and also dismantleable to the extent possible. It was a self-locking winch which was electrically operated. Now, it had 3 degrees of freedom. It was mounted on a plate which allowed a rotation of 360 degrees. Then the Teflon tether guide or rotating fork was such that it could rotate by approximately 270 degrees, so that when the aerostat starts moving, it will automatically align and not create stress on the winch. Plus, there were pegs for securing on the ground so that we can mount it on the uh, ground wherever we are doing our experiments. Otherwise, there is a danger that this whole winch could be pulled out and lifted by the aerostat in case of any vertical gust. So here are three images of our first trial, which was conducted in Ahmednagar um, in association with an industry partner. During this trial, we did not have the outer envelope. We only had the inner envelope, and we experimented with a ribbon structure. So we thought that to reduce the weight, we might be able to create a ribbon structure, and all the loads would be on the ribbon, and the envelope would only work on the gas handling. Now, this experiment taught us that that may not be a good idea, because as you can see, the envelope tends to bulge out from the borders of the ribbon, and that can cause local stress. And if not handled carefully, this local stress can lead to weakening of the inner envelope or even tearing of the envelope. So, since this was the first trial, it was mainly for us only and not for our sponsoring agency. It was held in Ahmednagar in under controlled conditions. So you can see that there was a cell on wheels that was installed at the location temporarily, and from that cell on wheels we collected this tether, sorry, the RF cable, mounted the Omni antenna. But in the middle picture, you can see that the Omni antenna actually is, not as a plumb line vertical. So this is a mistake in the mounting. This is what we learned during our trials, that we have to have a kind of a bearing at the bottom so that the antenna always remains vertical. Okay, I'll try to show you a small video. I would like a confirmation that the video is with.
Yes, sir, it is.
So there you see, this is the dismantleable ground control station, which is at sample. There is the winch in the center. Then this is the ribbon with the envelope. The ribbon inside over the envelope, and then you inflate the envelope. Now this is the attachment of the load bay. During night time, we are deploying it. So we had installed some LEDs on the ribbons so that there can be nighttime illumination. This is the next day early morning video. And now you will see the mounting of the Omni antenna and the RF cable. Yeah, so this is the RF cable which is slowly being released. Okay, so you can now see the system has been now deployed with the telecommunication link. The balloon height is approximately 65 meters above the ground level. So we are awaiting the results of the trials. We also mounted a monitoring station on board. This is the third day morning. And this is the aerial shot using a drone of the system in a deployed condition when the wind was in one particular direction. So you can see the sail is gathering the wind and allowing it to be stable. Okay. So after this first trial, we realized that the outer envelope had to be made from a parachute type of cloth and not from the ribbon. It will be difficult for any other agency to handle it. So we made some changes. But before that, we wanted to check whether it is effective or not. So we got some testing done by Reliance Geo. So you can see in this picture that our aerostat is deployed, and then all along nearby on the roads, this assessment vehicle would go and would try to establish communication with the balloon. So wherever they have line of sight, they were able to get good coverage. And in areas where there were obstructions, they were not able to get. So the red areas are the areas where there is obstruction. So for example, behind the field where we were doing our trials, there were some hills. So whenever the aerostat was not visible because of the hills, there would be break in communication or no communication. But whenever it was clear, you were getting a green signal. If we had raised the balloon above the height of the hills, we would have got communication, because you can see there are these green patches even very far away from the aerostat where you have these green patches. So which means communication is possible even at such a long distance. This is the numerical data which shows various distances, from the site at which you can see 1.3 kilometers, about 600 meters, 270 meters, even 1.5 kilometers, point number 12, we were able to get communication. Okay. So this was from a height of 50 meters. Okay. So when you have a height of 50 meters, you are able to communicate with an area which is at least 1.6 kilometers away. And the red patches are showing weak coverages because of blocking on the on-road signals. So what are the observations of this trial? First of all, we were able to deploy day and night without any break for around 4 days. Okay. And during this particular time, wherever their communication was established, there were no breaks reported. Okay. But as I mentioned, the antenna attachment had to be modified because it was not keeping vertical. It was getting inclined. It was fixed rigidly to the payload bay, and therefore, whenever the payload bay would be inclined because of the wind, the antenna also would be inclined. So we wanted to go for a plumb line fitting arrangement so that we can get a better radiation pattern. Now, with all these learnings, we did the second trial, which was in June of 2018. This was conducted in front of the office of the agency which had sponsored the project, that is the ITDA. You can see in the bottom, on the right side picture, the balloon installed in front of the ITDA building. So on the left hand side, you can see various things. You can see the two chambers, then balloon being inflated, and then we have a weather and the ground monitoring station. I will show you a small video. So this was a day and night operation for about 1 week. And since we were located near the chief minister's residence, there were helicopters flying. So we had to illuminate it whenever there was a reported activity. Okay, here is a picture of this balloon system, and I'm going to now show you a small video of the trial. Once again, a confirmation, please.
Hello.
I hope the video is visible.
Yes, sir, visible.
This is the weather station that you saw just now. This is the winch with the tether. Tether connected to the onboard avionics. Slowly, we raise the balloon using the winch, and then nighttime illumination. Next day morning, we were driving past. You can see the winds are not very heavy in the morning. Here is the Omni antenna with the camera. So it shows you how you can use the balloon for aerial surveillance. Now you can see the camera is the Omni. Now what you see now is three antennae given by CDOT for the Wi-Fi communication. Each of these is giving 120 degrees coverage. So with that you get a 60-degree coverage of Wi-Fi. So here are the results of our investigation. Our deployment duration was 72 hours non-stop. During this, we encountered a maximum wind speed of 40 kilometers per hour. The altitude that we deployed, we kept on changing depending on the requirements. And since we had a 150-meter long tether, we only went to around 144 meters. And we were able to establish 2G, 3G, 4G data and voice communication as well as Wi-Fi communication. So with the RF antenna, we were able to show that more than 2 kilometer radius, you can get communication uh, through SMS or through phone voice. With the sector antenna giving Wi-Fi, we could cover 1 kilometer radius or more. But with the police wireless antenna, we were able to communicate a distance of 60 kilometers, which was a very encouraging result. Okay. Now, I have some homework for those of you who are interested. But I would like to first quickly take any questions anybody might have. If there are people on board, I'd like to know if there are any questions. If not, then we will go ahead and I would like to show you uh, some data which I think can be used by you for doing the sizing of this particular system, because you've already done the portion related to the static lift estimation and static lift variation. So are there any questions? Can we quickly take any questions? All right, let's go ahead. So here is the data that I would like to share with you. This is the input data for you. So you can go through the floating altitude. So basically what I want you to do is, if you are interested to test your own knowledge about LTS systems, I would like you to size the aerostat to meet these requirements, and then we will compare our notes. Okay. So design an aerostat system to float at 60-meter. Okay, the envelope will have a slight overpressure of 500 newton square. It will have 99% gas at the beginning. The gas leakage rate is very small. The antenna is 4 kg and the RF cable, which was 133 grams per meter. This is the information regarding the latitude and longitude of the location and the temperature. So this will help you in calculating the effect of superheat. These are the details of the ribbon. Of course, this video will be shared on YouTube, so you can pause and you can read these data. So we are giving you the complete geometry of the ribbon, which is made up of 33 grams per meter length, running length material. This is the oblate spheroid geometry. Then there are formulae for its volume and surface area. And this is the material data. Okay. So there are 8 confluence lines. There are 4 handling lines. There are 2 safety lines. Then there is a sail, which is an isosceles triangle. Inner envelope 100 GSM. Tether 5 grams per meter. Now, these are the tasks that I would like you to do. Okay. So first of all, you need to calculate the mass of the whole system. Then you have to look at the mass of the other supporting systems, calculate the maximum and minimum net static lift, calculate the percentage loss in the stiff because of the change in the temperature or other conditions, look at the maximum and minimum tension, look at the maximum and minimum ballast required to maintain tension of 10 kg, and repeat if the lifting gas is changed from helium to hydrogen. Okay, so thanks a lot. Now I'll go back to the presentation. So the next item on the agenda was to look at the questions from the Excel spreadsheet. For your information, there are 848 students who are enrolled in this course, and out of that, 182 students have registered for the examination. However, in the first interaction session, it is sad that there is only one query. Only one question has been asked, and that too was asked only last night at around quarter to 11. Okay. But thanks to our teaching assistant, who is super efficient and super motivated, we have been able to accommodate this query in our presentation. The question has been asked by Ms. Anamita Bhattacharya. She wants to know, if an airship is stuck in some adverse weather condition, then how would the airship maintain its position and shape? Now, the answer is that an airship cannot maintain its position and shape if it is in adverse weather condition that causes change in wind direction. Now, this adverse weather condition is a difficult thing to quantify. For airships and any LTS systems, the main problem is changing wind direction. If you have a constant wind, let us say if you are having a sea breeze or a land breeze, you will be in a position to fight it to some extent with the propulsion system that you have. But there is a limit to how much you can fight. Okay. So, but with airships, there is an advantage which we don't have in the case of aircraft or helicopters. In case of aircraft and helicopters, when they encounter the weather conditions, the only option they have is to either head back or to circuit the weather and take a longer route and bypass the weather. In case of airships, you have an ability of maintaining hover for a very long time without little or no fuel consumption. So, if an airship encounters bad weather condition, it is possible for the airship also to divert, or it may even just wait and let the bad weather pass away. Because weather conditions may not necessarily remain bad weather for a very long time. Okay, it may sound very old fashioned, but you can just wait before you encounter the bad weather. You can wait, and after about an hour or so, when the weather conditions improve, you can go through. This facility is not so easy for helicopters because they consume massive fuel when they hover. And for aircraft, it is just not possible because it has to fly at some minimum speed to maintain lift equal to weight, and that too safely. So with airships, although you have larger weather sensitivity, you also have the ability to wait for the bad weather to pass. But if you are stuck in some weather condition, you cannot do much. You have to just get down or deviate. Now, some of you might be wondering how to ask queries. Okay. Maybe you have already been told, but I will reiterate that
Sir, are you presenting something?
whenever you get a mail containing the announcement of the live session, there is always a link in that to ask your queries. There is a Google form, and in that Google form, you can fill your queries and ask them. If you give us adequate time to respond to your query, then we can actually use the interaction session more meaningfully to include material or video or information or data or pictures or images to answer that query. If you don't give us time, then we will have to answer them verbally. And sometimes we can't take last minute queries. Okay, so please, you have an option to ask the queries in the Google form that comes with the announcement of the live session of the. Plus, there is always a forum. There is a discussion forum available on NPTEL for each course. In that discussion forum, you can actually mention all your queries. You can start a discussion on some topic, and therefore, uh, it is a continuous process, and the TA is available to answer your queries almost immediately on the spot without waiting for the next session. So please use the discussion forum actively so that the course becomes interesting not only for you but also for me and the TA. We have been doing this course for last many years. We also want to get some interesting queries and questions which increase our own understanding and appreciation of the subject. So we urge you to use discussion forum actively. Okay. Many of the queries that you will raise can be handled by the teaching assistant. In case there is a problem, then he is going to consult me. Then we also want you to give us feedback and suggestions regarding anything that we are doing which could be done better. We are very much open to constructive suggestions and feedback that can help us improve the course and do things which make it more interesting and a better learning experience for you. After all, the whole purpose of NPTEL course is to reach out to the audience. So if you do not take advantage of this facility and if you do not really reach out to us, then we will be unable to help you. It is very difficult for me or for Norman to handle individual queries via email because we have our own, normal job which keeps us occupied. But since we have volunteered to do this, we would like you to take advantage of this facility of NPTEL to interact with us. And we are always ready for getting ideas and suggestions for improvement. And also, if you happen to have any complaints, any form, any way, any kind of complaint, this is also a good way of communicating with us. So I would like to open the floor for any queries. I don't know actually how many people are there online in this session because at the moment I can only see the PPT. I cannot see the screen. Okay. So thank you for your attention and I wish you very happy learning with NPTEL. And I'm going to stop the presentation. Yeah, and I'd like to know if there is anything that I could. On the chat window, I see there are some entries, but unfortunately, while I'm presenting, I will not be. I would not be. Oh, I'm sorry. It is not Miss Anamitra Bhattacharya, but Master Anamitra Bhattacharya. I'm sorry. Really sorry about that. Okay. Okay. And regarding the examination pattern, don't worry about it right now. That is not really very important at the moment. At the moment, what is more important is for us to interact. Okay, so looks like we have only one person in the meeting, and that is Anamitra, and I'm sure is the same person who has been in touch with me. Okay, so maybe you can unmute yourself and tell us if I'm right.
Sorry, sir. Can you repeat kindly?
Yeah, so we have been in touch, correct?
Yes, sir.
Okay, fine. So I remember you are doing some kind of a internship where you are looking at OpenVSP.
No, sir. Actually, I was doing something regarding UAVs, and that time you had suggested me to work on OpenVSP.
Okay, fine. All right, actually, I don't have anything more to present or discuss, so maybe we can stop this session and we will meet again in the next session, which will happen. Uh, Naman, can you please announce when will be the next session planned? I think it is somewhere in March, right? Yeah, it's on 19th March. It's on 19th March. And the timing of that session, Naman, it's evening 4 to 5 p.m. Okay. So on 19th March, evening 4 to 5 p.m., we'll have the next session. So till then, I would like to say goodbye to you. Thank you so much.
Hello, so we are closing this session. Thank you.